The RL circuit in the picture is closed at t equals 0. What is the power supplied by the battery at that moment at t equals 0? At the very beginning, because of the inductor, the current will be equal to 0 in the circuit. And the power supplied by the battery is equal to the EMF of the battery times the current in the battery's branch. Here's the formula for the power supplied by the battery. It's EMF times I. Because I is equal to 0, the power supplied by the battery at t equals 0 is equal to 0. Of course, a moment later, the current will grow and the power will become non-zero, but at the very beginning, the power is 0. What is the energy stored in the inductor when the current has reached its steady state value, which is the final value of the current? In its final value, the inductor will act like a short circuit and its current will be equal to the EMF divided by the resistance. And the energy stored in the inductor at any given moment is equal to L times I squared divided by 2. L being the inductance, I being the current in the inductor. So let's substitute EMF divided by R for the current because we want the maximum value of the current. Here I have substituted EMF divided by R, that's the steady state value for the current. After the numerical substitution, we get 1 joule for the energy stored in the inductor. What is the power dissipated by the resistor when the current has reached its steady state value? The power dissipated by the resistor is equal to, again, its voltage times current I. And the voltage of the resistor by Ohm's law is R times I. So for power, we get R times I squared. Again, let's substitute EMF divided by R for I because we're interested in the steady state value of the current, which is the final value. Simplifying that expression, we get P equals EMF squared divided by R. And numerically, we get 4.3 watts for the power dissipated by the resistor once the current has reached its steady state value. What is the power supplied by the battery when the current has reached its steady state value? Again, the formula is the same for power. The voltage across the battery times the current at that moment. Voltage across the battery is the EMF, and the current is equal to EMF divided by R. When we simplify, we get the same expression as before, EMF squared divided by R. So the power supplied by the battery is equal to the power dissipated by the resistor, which is 4.3 watts. Does it make sense? Yes, because at this moment, the current has reached its final value. And the inductor is no longer storing any more energy. It has stored the maximum energy it can. All the power supplied by the battery is going to the resistor and it gets dissipated by the resistor.